Okay, so we are going to look at the next two sections of the further kinematics chapter. So first of all, we're going to look at kinematics and vectors within projectiles. So far, when we've done projectiles, we have split them into horizontal and vertical components. Now, in some circumstances, you don't have to. And basically, this example is looking through when you can use it in a vector form, partially when you have to and partially when you can do, for a projectiles question. So there's only one example because there's not actually any new content. It's just approaching the same style of questions but with vectors. So a ball is struck by a racket from a point A which has position vector 20j meters relative to a fixed origin 0. Or I shouldn't say 0. So if A is here, if that's 20j, that basically means it's 20 meters because j is 1 unit vector in that direction and the 1 unit would be 1 meter. Immediately after being struck, the ball has velocity 5i plus 8j meters per second, where I and j are unit vectors horizontally and vertically, respectively. After being struck, the ball travels freely under gravity until it strikes the ground at point B. Find the speed of the ball 1.5 seconds after being struck. So speed means we initially need to find the velocity, so we can then use it to find speed. So I'm going to resolve vertically. So my initial velocity is 5i plus 8j. My acceleration, well, I know that it's g. As a vector, g is only acting vertically, so there's no horizontal movement, and it's moving vertically at 9.8. Now, it's plus or minus 9.8 depending on your definition. Here it's going to be minus 9.8j. Okay, so it's minus 9.8 for every unit of j in that direction. We know that the time is 1.5 seconds and we need to find the velocity after that time. So v is equal to u plus at. So u plus at. So 5, 8 plus, and I'm going to put this back into a column vector. I don't really know why I did it that way, because it'd be 0i. Negative 9.8 times by 1.5 is negative 14.7. So therefore v is 5i minus 6.7j meters per second is the velocity. We need to find the speed, so we need the magnitude of the velocity. So square root 5 squared plus negative 6.7 squared, which is 8.36 meters per second to 3 significant figures. So far it's mostly using vector knowledge, really, and just interpreting this in terms of vectors rather than resolving horizontally and vertically. Find an expression for the position vector r of the ball relative to O at time t seconds. So because we have got the projectile travelling from point A, at the moment we can only really calculate displacement from A. Then we can use that to make it define displacement relative to O, because effectively it's going to work. Its displacement from O is always going to be 20j more than the displacement from A, whatever position it is. So we're going to do CVAT to find displacement. So I'm going to say displacement from A, and that's going to be equal to ut plus half a, or half of a is 0, negative 4.9 t squared. So this is my equation for that. I'm going to write it in terms of I and j, and this time, because I know that I need to then move it relative to o, which is 20j. So that's 5t, lots of I was about to write plus 0, obviously don't need to do that, plus 8t minus 4.9t squared, lots of j. So r, which is the expression for the position vector, is going to be equal to our displacement from A plus 20j. So therefore r is equal to 5ti, because there's no additional additional parts added to the I component, plus 8t minus 4.9t squared plus 20 lots of j. So it's a very complicated expression, but it is an expression for the position vector r. Part C. Hence, determine the distance OB. If we look back at our diagram, our distance OB is our horizontal displacement. Now, our horizontal displacement from O would mean that the j component here is 0. This will allow us to find t to then find a horizontal distance. So it would be 0j. So therefore 8t minus 4.9t squared plus 20 is equal to 0. I'm going to solve that on my calculator. And I get t is equal to 2.995, or t is equal to negative 1.36, which obviously is not a solution. So therefore OB is equal to 5t, because it is the I component. So it's 5 times 2.995, blah, blah, which is 14.975, which is approximately 15 metres to 2 significant figures. So this is where these problems start to get quite hard, because you're doing a lot more vector work and interpreting things in terms of a lot of vector language. So we have a lot more unknowns in our equations than we would otherwise. But the actual concept of projectiles isn't any different, which is why they've done it, only done one example. So for the second part, we're going to look at variable acceleration in 1D. Now, we've done variable acceleration in one dimension, but what we haven't done is variable acceleration when we have more complicated derivatives and integrals. So when you did the year 1 mechanics, right at the beginning of learning mechanics, as far as the book was concerned, because I was doing year 1 content, you'd only done polynomial, even though in reality you hadn't. But this time we're looking at more complex integrals and derivatives, and that's basically the only difference in this chapter, or in this sub-chapter. It's just actually going to be quite a good revision of pure content, which is really good, especially if we're moving on to further maths soon. So, first example for this one. A particle is moving in a straight line with acceleration at time t seconds, given by acceleration is equal to cos of 2 pi t meters per second squared, where t is obviously greater than or equal to 0. The velocity of the particle at time t equals 0 is 1 over 2 pi meters per second. Find an expression for the velocity at time t seconds. Well, velocity is the integral of acceleration with respect to time. So it's the integral of cos of 2 pi t dt. Now, whether you would do this just inherently or whether you'd use substitution, however you do it, this would become 1 over 2 pi, lots of sine 2 pi t plus c. If you're not sure about this, imagine that is 3x, 2x, something like that, to make it easier to think about what you would do if you were integrating that problem. Now we know that v is equal to 1 over 2 pi when t is 0. Sine of 0 is 0, so this whole concept will be 0, so therefore c is 1 over 2 pi. So therefore v is 1 over 2 pi sine 2 pi t plus 1 over 2 pi. I am going to factorise it because I just think that's easier to write rather than writing 1 over 2 pi twice. But that would be an acceptable answer. So that is our expression, and that is metres per second. B, find the maximum speed. So I did it slightly differently to the book because my automatic thought is that the maximum speed is found at when the derivative of velocity is equal to 0. So therefore, when a acceleration is equal to 0. So therefore, cos of 2 pi t is equal to 0. 2 pi t is equal to pi over 2, so arc cos of 0 is pi over 2. Obviously, I know that I'm dealing with radians rather than degrees because, evidently, I am, in the equation that's been set out for me. So, therefore, t is equal to a quarter. I would substitute this into my velocity equation. So velocity is 1 over 2 pi, sine of 2 pi times a quarter, all plus 1. Try that onto my calculator. And actually the calculator won't give it me as an exact answer. If you work the parts out separately, you get 1 over pi, which is 0.318 to 3 significant figures. Now this is what the calculator gave me. My calculator effectively won't write with pi as a denominator, so therefore it automatically gave me this. This one's Buddy. Don't think you can quite see him, I'm not quite sure. So I apologise for the purring over my voice. Hello. So this is the way I did it, because this to me was automatic. However, what you can do is know that if velocity is at maximum, so velocity is 1 over 2 pi sine of 2 pi t plus 1, well, the maximum that sine can be is 1. So this, when it's at its maximum, is 1. 1 plus 1 is 2. 1 over 2 pi times 2 is 1 over pi. So you could have thought about it in that way as well, but my natural instinct was to do this way. So both work, depending on how you want to work it out, basically. You are, hello. He has not left me alone all day. It's been like having a child climbing on me. Gets off my jumper. Right, there we go. Right, part C. Find the distance travelled in the first 3 seconds. So, distance travelled is obviously the integral of v, and if it's in the first 3 seconds, it's between 0 and 3. So I'm integrating 1 over 2 pi sine of 2 pi t plus 1 with respect to t. And I'm obviously going to take the 2 pi out because it makes it much simpler. Now, whenever you're going to integrate, you really do want to think about area. So you can sketch, and I usually encourage you to sketch diagrams for integrals. For one like this, you can potentially just picture it. So let's say it was sine x as a start with. Sine of 2 pi x, or any coefficient of x inside of our function, is not going to impact our y axis, our y values. So that's still going to be as normal, whether it's, no matter how it's stretched or enlarged horizontally, it's not going to change vertically. But then it's had plus 1. So I know that the minimum value of a sine graph is -1. When I then translate that up by plus 1, the minimum is going to be 0. So the whole graph is going to be above the x-axis. Therefore, we don't need to worry about this. If there are parts that are underneath the x-axis, then obviously we would want to cut it up, integrate it between the two parts, and do it that way. It says find it. So just type this into your calculator. So integral button. So sine of 2 pi alpha x. Oh dear, I didn't do the 2 pi button right. 2 pi x. Why is that not working? There we go. Brackets plus 1. Then I'm going to go back to fill in those. So that is 3. 1 over 2 pi times 3 is 3 pi over 2, which is approximately 0.477 metres to 3 significant figures. So, not too bad. Not too bad. As long as we can differentiate or integrate those, then the actual concept itself is not a challenge. So, final example. A particle of mass 6 kilograms is moving on the positive x-axis. At time t seconds, the displacement s of the particle from the origin is given by s is equal to 2t to the power of 3 over 2 plus e to the power of -2t over 3 metres, where t is greater than or equal to 0. Find the velocity of the particle when t is equal to 1.5. Well, I know that the velocity is the derivative of displacement, so I'm just going to derive this. 2 times 3 over 2 is 3, t to the power of half, minus 2 lots of e to the power of minus 2t over 3. So that is our velocity equation. I want velocity when t equals 1.5. Sub that all into my calculator and I get 3.64 metres per second to 3 significant figures. Part B. Given that, sorry, my phone's going off, I will answer that in a minute. Given that the particle is acted on by a single force, oh, I just shut my door so it's not quite so loud, and the cat will probably freak out because I've shut the door. Given that the particle is acted on by a single force of variable magnitude F newtons, which acts in the direction of the positive x-axis, so it's basically telling you it's horizontal, find the value of F when t is equal to 2. We are in mechanics. We can never forget force equals mass times acceleration. If we think about this problem without it, we have no way of working it out. So, I need to work out the acceleration formula, which is the derivative of our velocity. So I'm going to derive this equation, which is 3 over 2 t to the power of -1/2 plus 4/3 of e to the -2t. So I want acceleration when time is 2 seconds. So I'm going to substitute that into this equation and I get 1.085, etc., showing the examiner that I'm using all my values. Therefore, the force is equal to the mass, which is 6 kilograms, times my acceleration, 1.085, which is 6.51 newtons to 3 significant figures. So most of this chapter is going to be, or this section of the chapter is going to be basically you revising pure, but in a mechanics context. But then they will be adding some specifically mechanics elements like force equals mass times acceleration. So those parts are really important for you to think about. So that's work for you today, and we'll move on to the last couple of parts towards the end of the week.